The objective of this video lecture is to discuss the learning curves of the various PV technologies. And how do these curves relate to the market shares of the various PV technologies? All the technological advances and upscaling of production of solar modules have resulted in an impressive learning curve for PV technologies in general. In the last 42 years, the cost price of PV modules has reduced by an impressive factor of 300, while the cumulative production has increased by an impressive factor of 5 orders of magnitude. But we have to realize that the module is only one component of the total PV system. The cost of the PV system will determine the cost of the solar electricity generated. Here we show the learning curve of the total PV system as well, based on the market prices in Germany. As the cost of the PV system is the module cost plus all other costs, I call them for simplicity non-module cost. Here we show the PV non-module cost as well. As we can see that for a long time the module has been the dominant component that determined the cost price of the total PV system. Nowadays the module contributes to less than half of the cost of the PV system. This is the reason why the efficiency of modules are important if we look solely to the metric of cost price of the solar electricity. Since the cost of the total PV system consists out of the module cost and the non-module cost. The non-module cost, often referred to as balance of systems, includes the racking, the inverter, cabling, maintenance, battery, etc. For simplicity, we assume that the non-module costs are the same per square meter for all type of PV modules. A module with a higher efficiency will have a higher nominal power output per square meters. This means that the non-module cost per generated power will go down as the module has higher output for the same amount of cost. This results in a lower price per watt peak for the entire system as well. Let's for example compare thin film silicon and a thin film cadmium telluride module encapsulated in glass. They are the same type of products, however the cadmium telluride module will result in lower non-module cost due to its higher module efficiency. The big question is, when will the learning curve stop or level off? This gives a wide margin of uncertainty. A wide range of cost prices at a certain cumulative installed power might be possible. Let's consider that we would install a PV system in a region which has on average a daily solar radiance equal to 5 equivalent sun hours. We would need a PV system cost of only 46 euro cents per watt peak to achieve an electricity cost price of 1 euro cent per kilowatt hour. If the learning curve the last decade would be extrapolated, it means that the milestone could be achieved before the terawatt limit is reached, so within the next 10 years. However, it could be that the learning rate would slow down. The non-module costs have a lower learning rate than the modules. This could slow down the learning rate of the PV costs. The learning rate, by the way, is the fraction of reduction in the cost price if the cumulative production doubles. Lower learning rates would take a longer time to reach the milestones of 1 euro cent per kilowatt hour. In climates with on average a daily irradiance of 4 equivalent sun hours, the cost price of the PV system has to be 37 euro cents per watt peak to realize the 1 euro cent per kilowatt hour. It would take even a much longer time to reach this milestone in these regions. And let's consider regions in the northern or southern hemisphere at higher latitudes. And let's assume they have an average daily irradiance of only 3 equivalent sun hours. The cost price of the PV system would need to drop to 28 euro cents per watt peak to meet the 1 euro cent per kilowatt hour magic boundary. It would take an even longer time to reach such a milestone in these places. Currently, we have seen tenders on large-scale PV utility in Dubai and Abu Dhabi, where solar electricity will be delivered at cost prices below $3 per kilowatt hour. How are these low costs for solar electricity realized? One of the reasons next, of course, a local high solar irradiation is that these low prices have been achieved due to availability of cheap financial resources, or in other words, low costs for investments. However, in less sunny regions like Denmark and Germany, tenders of 5 € per kilowatt hour for large-scale utility solar electricity has been achieved as well last year. How does this compare with the cost of electricity generation of other methods? For this comparison, we look at the levelized cost of electricity, or LCOE. The LCOE is an economic assessment of the average total cost to build and operate a power generation asset over its lifetime divided by the total energy output of the asset over that lifetime. You can see that the renewable generation methods like wind and solar electricity on utility scale in sunny regions have become already competitive with fossil fuels. LCOE of electricity for a solar farm in Germany was 5 to up to 8 € per kilowatt hours, as stated by Fraunhofer ISEN in their recent PV report. However, keep in mind that the LCOE is not the only dominant aspect. Distribution and storage of energy reliability, subsidies, taxes, and government policies are important factors that determine the contribution of the various energy sources to the energy market. However, cheap wind and solar electricity demonstrate that the technical challenges are moving to the distribution and storage of these cheap electricity sources. Let's go back to the different PV technologies. What are the current market shares? Crystalline silicon is the dominant PV technology. In 2016, it had a market share of 94%. 70% of the market is multicrystalline silicon modules and 24% is monocrystalline silicon modules. All thin-film PV technologies together had a market share of only 6%. It even dropped 1% in reference to the last year. The same report makes some claims on the energy payback time of PV systems. The energy payback time is the correct time a PV system has to operate to recover the energy that went into making the system in the first place. The energy payback time is dependent on the geographical location. To get some feeling for it, I will give some examples from the Fraunhofer report. PV systems in the Northern Europe need around 2.5 years to balance the input energy, while PV systems in the southern part of Europe equal their energy input after only 1.5 years or even less, depending on the technology installed, of course. For example, a PV system located in Sicily with multi-silicon modules has an energy payback time of around 1 year. Assuming 20 years lifetime span, which is quite conservative, this kind of system can produce 20 times the energy needed to produce it. So, what are the difference in the cost price between the various PV technologies? When I was a student, the different generation of PV technologies were explained by this graph introduced by Martin Green from the University of New South Wales. It worked very well for a long time, but the current learning curves will challenge this graph, as I will explain. On the horizontal axis, the cost price of the solar cell per area expressed in $ per square meter is plotted. So solar cells made of expensive materials or using expensive processing methods will be further to the right on this axis. The conversion efficiency is represented by the vertical axis. The efficiency scales with the energy yield of the solar module, or with watt per meter. It means that the slope of the dashed line is equal to watt per dollar, or in other words, it's reciprocally linear with the cost price per watt peak. The cost price per watt corresponds to the cost price of the energy generated by the solar cell. If the slope of these dashed lines is very steep, the cost price per watt is low, whereas when the slope of the dashed line becomes less steep, the cost price per watt peak is getting significantly higher. To compete with other energy sources, you would like that your PV technology overlaps with the steepest lines in the graph. The first generation PV technology corresponds to conventional crystalline silicon wafer technology with a relatively high conversion efficiency. 2 decades ago, crystalline silicon had a relatively high cost per area. The light gray circle roughly shows the area of which you would find the first generation PV technology. The second generation PV technology corresponds to thin film PV technology. The less material and cheaper process technology used makes the solar cells cheaper. Nevertheless, due to the low cost, the cost price per watt peak of the second generation PV technology was expected to be significantly lower in reference to the first generation. The blue area represents the so-called Shockley-Queisel limit. The definition of the third generation PV technology is based on solar cell concept which try to tackle the Shockley-Queisel limit. So third generation PV technology would be solar cells with higher conversion efficiencies in reference to the first and second generation, while the cost price of the materials and processing techniques used to process the third generation solar cells are expected to be cheap. The third generation solar cell technology was expected to overlap with the steepest dashed lines in this graph, meaning that the third generation technology would have the lowest cost price per watt peak. However, these predictions did not hold. In reality, the cost price of crystalline silicon has come down to so much that it's even lower than the thin film PV technologies. Third generation concepts beyond multi-junctions and concentration concept have not realized high conversion efficiencies yet or low processing costs. Therefore, the first generation PV technology still is the most cost-effective one. This can be nicely illustrated as we look at the learning curves of the 3 most dominant PV technologies on the market. Here you see the module cost of the total market. And here you see the module cost of the various crystalline silicon modules as reported in the shown references. The data includes cost prices up to 2014, by the way. The learning rate is the relatively drop in cost price when the cumulative production doubles. The learning rate for crystalline silicon is roughly 23%. If we look at cadmium telluride, the data is from First Solar, by the way, we see that at lower cumulative production, lower cost prices per watt peak are realized at small production volume. This is indeed in line with the second generation PV technology. However, the learning curve is smaller than for crystalline silicon technology. It's only 16%. This does not mean that the cadmium telluride PV technology is inferior to the crystalline silicon technology. This difference has to do with the benefit of scale. The smaller global capacity of the cadmium telluride PV production gives less benefits of the economy of scales, such as lower prices for bulk deals on materials, equipment, etc. First Solar is constructing new production line that can handle much larger size panel. That will significantly increase their economy of scale. If we look at CIGS, we observe a similar trend. Lower cost prices per watt peak have been realized at very small production volumes. This is indeed in line with the second generation concept. However, the learning curve is smaller for the crystalline silicon technology. It's 8%. The difference has again to do with the benefit of scale. The smaller production capacity of CIGS PV gives less benefits of the economies of scale. But is high efficiency and cost price the only design or market metrics that is important? We will discuss that in the last video lecture of PV2X.